Thanks, Denny. So today I want to talk about this concept that Matei started to introduce this morning in his keynote, and the idea is structuring Spark. This is something that we've been doing since we first introduced Spark SQL into the Apache Spark stack, about, I think it was 2 years ago. Since then, we started with SQL, we moved on to DataFrames, datasets, and now we're doing streaming. And in this talk, I want to kind of discuss what I mean when I talk about structure and why structure is important. Why telling Spark more about the structure of your computation can actually allow Spark to execute your code more efficiently. So before we dive into kind of all of the newer APIs, I want to start with a little bit of background on what I mean by unstructured, kind of in contrast. So a little bit of background, what exactly is going on under the covers when you create an RDD? So there's a couple of things that define an RDD. One is the dependencies. So I have an RDD, and it's reading from these text files or this other map operation or something like that. So it's a list of other RDDs that this one needs in order to compute its result. And then the next part is partitions. So given these dependencies, how am I going to split the work up? How am I going to take this computation and parallelize it across the cluster? And sometimes this can also include locality info. So for example, if your RDD is reading from HDFS, it'll include the names of the machines where those blocks are located, so the Spark scheduler can be smart and put that work right next to the data so it doesn't have to transmit it over the network. And then finally, you have this compute function, which is really just a function that goes from a partition description. So it could just be the name of a file, or it could be an index or something like that. And what it needs to do then, given this partition, is produce an iterator of the data that's actually going to be stored inside of the RDD. So this is actually a pretty simple API, and that's really where its power lies. In fact, all of Spark SQL and DataFrames and structured streaming and even DStreams was all implemented on top of this RDD API. But what's wrong with it from a programmer perspective? So first of all, the computation itself is opaque. Spark has no idea that you're doing a join or that you're doing a filter or which columns you even care about inside of that computation. It's a black box. All we know is that when we call it, it's going to return an iterator to us. And then the next thing is the data itself is also opaque. We just know that you're giving us an object, either in Scala, Java, or Python, and the only thing we can do with that object is take a serializer and turn it to bytes. We can't look at individual columns, we can't reformat it, we can't do special compression like run length encoding. And as a result, the kinds of optimizations that we can do are pretty limited. You're kind of dealing with gzip and cryo, and that's about as far as you can push the performance envelope. So in contrast to the RDD API, I'd like to describe what I mean when I say structure. And kind of the idea here is we're going to take your computation and we're going to arrange it according to some kind of a plan. And really the right way to think about this is kind of common patterns of data analysis. We're going to define a couple of common patterns and let you describe your computation in that way. So filtering, selecting, aggregation, joining, those kinds of things are now these higher level operators that Spark might understand. Now, why do you want a structure? I've been kind of hinting at this. But by definition, when we apply structure, we're going to limit what you can express. And that's actually maybe OK, because in practice, we can actually accommodate a vast majority of all of the types of computation that you'd want to do within this framework that we're going to construct for structure. It turns out many computations are reading data, joining, filtering, aggregating. And if your computation falls outside of that pattern, you can always use the escape hatch and go back to RDDs. Although personally, I find myself doing that less and less as the APIs get better and better. And really, the key idea here, the whole point, the reason we've been working on Spark SQL and DataFrames and datasets and structured streaming is by limiting the space of what can be expressed, we enable all kinds of cool optimizations. And throughout the rest of this talk, I want to kind of describe to you exactly what Spark is able to understand about your computation and how it affects the performance of your job. So before we do that, I want to do kind of a high-level overview of what the different APIs look like and why you might consider using them, in particular, how it relates to the kind of errors that you're going to get when you make mistakes in your program. So starting at the far side, we have SQL. When you write a SQL query, you are giving Spark just a plain string of text. The Scala compiler, the Java compiler, Python have no idea what's going on inside of that string, so you're not going to get any kind of errors until runtime. whether it's you're accessing a column that's not there, or you spell select wrong or things like that. Basically, until it gets to Spark, until Spark can process it in the middle of your computation, we're not going to be able to throw any errors. But at the same time, it's a very useful language. Tons of analysts know it. You can plug it into BI tools. So it's definitely great for that kind of analytics. Take one step closer to the type-safe, kind of more Java or Scala type programming, and you have this thing called DataFrames. So in contrast, if I call a function on a data frame, if I say select and I spell select wrong, the compiler is going to tell me, hey, that function doesn't exist. So you're going to get these kind of syntax errors automatically, even though underneath the covers you're constructing the same kind of thing you would be constructing with a SQL query. But if you ask for a column that doesn't exist, Scala doesn't know about that, Java doesn't know about that, so you won't find out until the query analyzer figures it out. And then finally, at the far other end of the spectrum, we have datasets. This feels a lot more like RDDs. You have typed objects that the programming language understands. So if you call methods on your object that don't exist, or you mix up types, you're going to find out about all of those kinds of things at compile time, as well as any other kind of syntax errors that the compiler would normally catch. So there's no one right answer. But really, it's about kind of what the computation you're doing, how to express it most easily. And so let me walk through a little bit more what each of these APIs look like. So starting with the Dataset API, this is type-safe objects, and you can operate on them with Lambda functions. So an example here is I'm going to take some data, and I'm going to read it in as JSON. You saw this earlier today at the keynote demo. And now I'm going to apply a class to it. I'm going to say I expect this JSON data to have two fields. It's going to hold people. People are made up of a name, which is a string, and an age, which is an integer. And just by saying as on the data set, Spark is going to automatically generate all of the boilerplate that's required to take JSON data and materialize it inside of this type-safe class. And this could be any kind of class. Here I'm showing Scala case classes, but this could also be Java beans or kind of other things like that as well. We support nesting and arrays and all kinds of things inside of dataset classes. And now that it's in the form of this object, I can work with it directly in the programming language. I can pass a Lambda function and say age greater than 30. It knows age is an integer. It's checking all of these things for me automatically. This is also really useful if you want to express code that is hard to express in SQL. So for example, I want to group by the name, and then I want to compute histograms. So that would be kind of difficult. You could do it in SQL. It'd be a pretty long select statement. But this is very easy to express with imperative programming. I can just say map groups, create an array of integers, and just assign them to buckets, and then return that object, and now you've got your histograms. So I think there's definitely a type of computation where data sets are the right way to express it. Now, data frames and data sets, this is something that's changed between Spark 1.6 and Spark 2.0. In 1.6, they were totally separate concepts, and the reason was we didn't want to break any APIs in the 1.x series. We were very serious about API compatibility. In Spark 2.0, we unify these. So there's no longer two distinct concepts for you to work with. It's just the same thing with two different flavors, depending on kind of what the objects are inside of it. The only things that we changed are if before you were calling .map, it was returning an RDD. If you want to do that now in Spark 2.0, you say .rdd.map. To tell us you want to escape back to RDDs. Otherwise, if you do map or filter any of these operations, it's going to return you a data set. It's going to kind of stay in the structured land. So what this means is a data frame is just a data set of generic row objects. When you don't know all of the fields ahead of time and you don't want to compile a class that's going to hold your data, generic row objects are definitely the answer. And so anytime you use stringly type methods where the compiler doesn't understand what's going on, it's just going to return you a data frame or a data set of rows. And you can always switch back to the typed representation by saying as and passing it a class. So a lot of times I get this question, what about Python? You've been talking about Scala and Java a lot. And my thought is, basically in Python, because of dynamic typing, you've always had a lot of the benefits of the Dataset API. So in particular, accessing the results of a data frame in Scala before datasets was really awkward. You had to access the columns by ordinal, so I have no idea what 0 is. Is that the name? Is that the age? I'm not sure. I guess it's a string, so it's probably the name. But if you get it wrong, you're going to get class cast exception errors at runtime. So this was always kind of awkward. But because of Python's dynamic typing, you've always just been able to access the fields by name. So there's not really a lot of reason to have this, although we're continuing to look at ways to make sure that all of the APIs are consistent and easy to use no matter which language you decide to work in. But really, I think a key idea here is no matter which language you use and no matter which API you use, so whether you're writing in Java, Scala, Python, R, whether you're using SQL, DataFrames, or datasets, immediately the first thing that's happening is you're constructing what we're calling a logical query plan. That's what tells Spark the structure of your computation. It says, take this data, read it from S3, do a join, do a filter, and then the optimization pipeline is completely agnostic to where that logical query plan came from. So no matter which language you're writing in, you usually get pretty similar performance. So now I actually want to dive into a couple of different types of structure and talk about exactly what Spark sees when you type specific types of code. So I'm going to start with computation. So, one example is columns. This is a very important part of the DataFrame and Dataset API, is basically a way to express a new value based on input values. So a couple of examples of a column. I can say, take the input value x, and check to see if it equals 1. So this is the DSL. This code will work in either, I think, Scala or Python. And I can do the same thing where I access it directly on the data frame. So it can be kind of just an agnostic column that's just a string, or a column where I'm saying I want x from this specific data frame. Another way you can do it is you can actually just use the SQL parser. All of these are equivalent, by the way. These produce exactly the same code underneath the covers for Spark. And so expr is basically an escape hatch into a full-fledged SQL parser that you can use from inside of the DataFrame API. So anytime you're working in DataFrames and you know the SQL way to do it, just use expr and you can type arbitrary SQL strings. You can type if statements, UDFs, all that kind of stuff works inside of here. And then another way is to actually just go all the way and write the whole thing in SQL. So select where x equals 1. But underneath the covers, all of these are going to produce expressions that mean check to see if x equals 1. And it's not just about very simple things like equality. Since Spark 1.5, we've had a pretty rich library of functions that you can actually compose. And the cool thing about this is you're not actually calling the function at analysis time on your driver machine. What you're doing is you're constructing instructions for the query planner about how to compose these operations, and then at runtime, it's actually going to generate efficient bytecode for the specific functions that you're calling. So all of these functions have built-in code generation capabilities, which is another thing Matej talked about quite a bit this morning during his keynote. So I think it's actually pretty nice to be able to take these functions and compose them and do fairly complicated things. A pretty common question I get is, people are coding in Python, and they say, what's the performance hit for writing this in Python instead of Scala? Well, if you use these functions, it's the same. It doesn't matter whether you're writing in Python, Scala, R, Java. It'll all execute the same efficient bytecode underneath the covers. So let's look at a couple of different ways to express something and compare how they're different. So if we look at a function that you type as a lambda function, x, pass me in an x that's an integer, check to see if x equals 1 versus a column. What Spark actually sees is completely different. In the case where you give it a lambda function, we just see that you've given a sum function that takes an integer and returns a Boolean. We don't know how you figured that out. That's kind of all we've got. But in contrast, if you specify it as a column, I actually understand. You're saying, does the column x equal the integer 1? And so that's a lot more information for the Spark analyzer to work with. And so why this is important, let me give you an example from our Postgres data source. So if I'm querying data from Postgres, I'm going to create a data frame Spark read, connect to JDBC, connect to this Postgres thing, and then on top of that data frame, using Spark, I'm going to apply a predicate. I'm going to say I only want records where name equals Michael. What Spark's actually going to do under the covers, because it understands that equality, is it's going to generate very efficient SQL that takes that predicate and pushes it down into the Postgres database. So no records that don't match your predicate will even be shipped over the network. This is much faster than doing the filtering inside of Spark. So understanding actually allows us to shift computation around in more intelligent ways. Another example is efficient joins. So in this case, I'm doing a join where I have a UDF that's just checking to see if two columns are equal. Unfortunately, Spark doesn't know what you're doing. This is actually a pretty common question on the user list. And so as a result, when I apply that filter, the only way for Spark to know which tuples are matching your predicate is to try every single possible combination, which is called a Cartesian product, and pass that to your function. So if you have two large tables, this is incredibly expensive. It's actually n squared. But if instead you specify this as a column expression, you say x equals y, what we're going to do is we're going to take the data, we're going to hash partition across the cluster using a shuffle, and then we'll build hash tables on either side to make sure that we can do this very efficiently. And so it'll actually end up being something like n log n if we use merge sort. And the key insight here, the thing that Spark understands, is if I take a giant data set and I sort it, if the columns are equal, they'll sort to the same place. And so now we can leverage that to do a much more efficient computation than the Cartesian product. So that's the idea with computation. But another really important part here is the data that you're doing the computations on. So Spark has a pretty powerful data model. I talked about it a little bit before. We kind of support all types of primitives, byte, short, long, integers, strings, binaries, booleans. But we also support complex data structures. So any of these data types, you can actually create an array of them. You can also create a struct. A struct is a fixed set of names with a fixed set of types. Or you can create a map, which is a single type to a single type, but an arbitrary number of columns. And by composing these, you could pretty much model many of the different cases. This matches Avro, this matches Parquet, this matches what you can do with simple case classes, this matches what you can do with Java beans. And so as a result, we can do a pretty easy mapping between these other types of data and the Spark data model. And the important thing, the reason that it's important for us to actually understand the structure of the data and be able to map it into our own type system is we can actually leverage that when we're doing encoding. So when we take data and we cache it in memory, or when we take data and we shuffle it over the network, we can use our own custom encoding that understands this structure. So this is an example of taking the data 1, 2, 3 and data in bricks and composing it into a single binary blob that we can efficiently serialize and ship over the network. And kind of the key thing here, this is a new concept that we introduced in 1.6 and that is very important in the API in 2.0, is this idea of an encoder. This means that you don't have to write that boilerplate code that takes your case class and turns it into JSON, or takes the JSON and turns it into your case class. What happens is we automatically take the structure of your data and we do code generation at runtime to build these encoders to do these types of translations. And so what the power here is that this actually lets you bridge these objects with many different data sources. So I've been using JSON quite a bit as an example, but it doesn't matter whether you're reading from any of the different data sources that Spark supports. So it could be JSON, but it could also be JDBC, Parquet, Avro, Cassandra. Pretty much all of these data models can be mapped into Sparks, and as a result, you get this translation automatically. So it's about more than just not having to write a bunch of boilerplate code. It actually turns out that you end up with significant space efficiency. So in this example, I'm caching a bunch of strings in memory. And it turns out that when you do caching with the JVM, it's incredibly inefficient. It actually stores it in UTF-16. It has a whole bunch of extra objects and headers and things to keep around. Whereas with Spark, we encode it much, much tighter. And we can actually just keep it in line with the rest of the data. So what you can see here is if I take the same data set, and cache it with RDDs instead of data sets, I actually need significantly more memory in my cluster in order to be able to handle that. And it's not only about the size when you're actually storing it in memory, it's also about the performance going back and forth between these representations. So a pretty common tuning tip, if you read the Spark tuning guide, is to take your Java serialization and switch it out for cryo. Cryo is a much faster serializer, although sometimes it doesn't work with certain data types, which is why it's not the default. But even if you compare to cryo, these encoders are actually significantly faster, both in serializing and deserializing the representation. And what this means is your shuffles can be significantly faster. And the reason for this, again, is code generation. We're doing this at the last possible minute after we understand the entire structure of your computation. We can build custom bytecode for that specific object instead of having some generic logic that understands all kinds of objects. So what this allows us to do, now that we've serialized the data, it's even more than just this performance. Given some data that's stored inside of Spark, there's often this question of, do we have to turn it into an object in order to do computation on it? So let me walk through an example that shows why we don't have to do that and why that's actually pretty powerful. So one example here is I'm taking a data frame, and I want to find all of the records where the year is greater than 2015. So I'm looking for fairly recent data. Spark is going to take this column expression, and it's going to turn it into this catalyst expression. Catalyst is the name of the query optimizer that runs inside of Spark. And so given this catalyst expression, we now understand that we're taking the year column, and we're doing a greater than operation on it, where we compare it with a literal value that's hard-coded into the code. And what Spark actually translates this to at runtime is this Java code. The way this actually works under the covers is we spit out Java code at runtime, and we toss it at a Java compiler, and we get back bytecode that we then actually execute. So let me kind of unpack a little bit what's going on here. So this looks pretty low level, and there's a good reason for that. We actually know exactly where in any record we need to jump to find it. And then we pull out the data, and then we do the operation we want. The important thing here is there's no allocations. We created no objects. You're creating no GC pressure. And as a result, this can run significantly faster than if it was your own Lambda function that was doing this comparison. And another kind of important detail here is this platform.getInt is actually what's called a JVM intrinsic. So what that's going to do is that's actually going to jit down to assembly that's pretty close to doing pointer arithmetic. We took our code generator and we compared it with some handwritten C++ code, and it turns out it's actually within 10 to 15% for a wide range of these types of predicates. So what that means is you're getting pretty close to bare metal without ever having to write anything lower level than just DataFrame code. So that's kind of the batch APIs, but now there's a question of how does this apply to streaming? And we've been talking a lot about structured streaming. I want to give just a little bit more background. There have been a couple of different streaming APIs in Spark. There was the dstream API, which was based on RDDs. The idea was micro batches, and it was very kind of low-level RDD focused. With structured streaming, kind of the vision here is we want to take the nice APIs that you have with datasets and DataFrames and allow you to do continuous applications on top of that. I want to explain why structure is actually very important to being able to do that. The key idea here is we don't want you to have to reason about the streaming, right? That's when you have to reason about streaming, you have to reason about fault tolerance, you have to reason about failures, and by letting the Catalyst optimizer do the incrementalization of your query, we can kind of push all of that burden onto the optimizer itself. And so what you end up with is you end up with an API that looks very similar to what you had before. You had data frames in Spark 1.3, and in Spark 2.0, you have continuous data frames, which are just data frames where data continues to arrive over time, and we process it incrementally as it gets there. And this is one single unified API. So kind of the high-level goal is, we want to be able to run most of the same queries. Now, another question that I get, and since it's the developer track, I'll go into a little bit of details, is like, how is that possible? You can't possibly incrementalize every query. And of course we can't. If you're doing a count to strength on an infinite stream, that's going to take infinite state, and we're not going to break the laws of physics. And so right now, we actually have what's called the unsupported operation checker. It's going to tell you, no, that's a bad idea. That's going to tip over. You don't want to do that. But the goal is to continue to expand this, to work on more and more optimizations so that we can actually handle pretty much most of the important queries that can run on top of data frames. Some key things that we want to make sure we definitely have in the API are event time, and that's event time in spite of late data. So if you saw the demo this morning, that window operation that we used in batch didn't care about late data. So when you use it in streaming, it shouldn't either. It should just always give you the correct answer, and if data arrives late, you should update the answer. And this is kind of the difference between traditional imperative streaming and a continuous application where Spark owns the end-to-end kind of completion of the stream. And the nice thing here is, now we can actually unify all of these different types of computation. I can aggregate data in a stream and then query it through the Spark JDBC driver. So if I'm constantly building up a table stored in some efficient format, I can query in real time those results using the Spark JDBC server. Another kind of nice thing, I didn't show this morning, but you can actually change queries at runtime. If you find a mistake, you can kind of restart the stream from a new point, changing it interactively. You can add and remove queries from a running stream without having to restart the entire context. And I think that's a pretty powerful thing when you want to explore data and kind of work with it interactively. Another key idea here that we're kind of just starting on, but I'm very excited about. Since Spark has long had this vision of being a unified stack, we're working very closely with the ML team to figure out how we can make it so that any of the machine learning models that support online learning kind of seamlessly be applied in the structured streaming context. So let me kind of just very quickly, for those of you who didn't see stuff this morning, talk a little bit about what I mean to take batch queries and turn them into streaming queries. So in this example, we're reading some JSON log files. We're doing a pretty simple aggregation. We're grouping and summing by time. And then we're writing it out to a MySQL database. So you could run this once, but then more data would arrive, and you'd have to run it again. And the problem here is you're actually rescanning all of the logs every single time. So as more and more logs appear, you're doing n-squared work just to keep this MySQL table up to date. And I've seen this pattern over and over and over again with the batch API. Once you answer a question once, that's never the end. You want to answer it multiple times. And watching people do the work to incrementalize themselves is actually pretty painful as a developer, because it's something that we should do automatically. And that's something that we're looking to do in Spark 2.0. So if you see, I just changed two things. Instead of saying load, I'm loading a stream. So this is telling the optimizer, when you go to that directory, scan it continuously. Don't read it just once. And then instead of running the query once and writing to MySQL, I'm going to actually start this stream. And that's going to return this continuous query handler that lets you control this query, which is running repeatedly in the background. So how does this actually work? Kind of the high-level idea, I talked a little bit about this before, is at the execution level, we have this kind of concept of a logical operation. So basically, this is like what the structure of your computation is. And then physically, we understand exactly how we're going to perform that optimization. And the trick here is we're trying to use the Catalyst optimizer to take that query plan and turn it into an incremental query plan. Let me give you kind of a relatively simple example here. Going back to the aggregation example that I just showed, let's say we take this data that scans S3 files, aggregates them, and then writes them out to MySQL. If we incrementalize it, we have to make a couple of changes. One is, instead of scanning all the files every time, we're going to remember the files that we read, and we're only going to scan the files that are new. Second is, when we're doing aggregation, we're not going to aggregate only the data that we see in that single query. We're going to take the results from all of the past queries that we wrote and sum them up together. So this is what we call a stateful aggregation. And then in the end, we just continually update MySQL as things, as new data flows in, instead of just writing to it once. So that's kind of a whirlwind tour of what structure means in Spark and what it means for streaming. There's actually going to be another talk about streaming immediately after me by TD if you want to learn more of the nitty-gritty details about what the API looks like. But before I wrap up, I want to talk a little bit about what's there and what the roadmap looks like. Since this is the developer audience, I know you were probably eager to get your hands on these new APIs. I want to make sure everyone knows exactly where we stand. So in Spark 2.0, kind of one of the main focuses was unification of DataFrames and datasets and all of the various Spark context, SQL context, Hive context, streaming context. And then the other thing is the basic streaming API. So we wanted to make sure the APIs we provided made sense and worked, and we have some basics of event time aggregation. But there's obviously a lot to do. Streaming systems aren't built in a day. And so in Spark 2.1, we're looking at adding a bunch of other stuff. So streaming sources and sinks like Kafka, integration with machine learning, and also the concept of watermarks. When I'm aggregating over time, I want to drop data that is super, super late so I can bound the amount of state that I want to keep in memory. And another thing that you'll be seeing kind of moving forward is more and more structure being applied to other libraries. MLlib pipelines are now built on DataFrames. GraphFrames is a reimplementation of GraphX on top of DataFrames. I think you're going to be seeing this as a pretty common theme throughout the Spark ecosystem. So I think I'm just about out of time, so I don't want to take you too much longer. I don't think there's a ton of time for questions.
No.
So we'll just end it. But I have an office hour at 2:45, which you should definitely stop by. And I'll also be doing booth duty at the Databricks booth at 5:45. Thank you very much.